We are very lucky to be joined by our three professor speakers earlier, Professor Chris Manning, Professor Emma Brunskill, and Professor Tengyu Ma. And then we are also joined by Samir Dhir, who is the president of Versusa Corporation, one of our industry members with the Stanford AI Lab. He's responsible for developing and executing Versusa's growth strategy and overall P&L management for all industry groups, including banking and financial services, healthcare, insurance and life sciences, telecom, media, and high tech. So we are very excited to hear more about research as well as sort of broad industry interests in applying these sorts of technologies. I think maybe we'll start with kind of a broad question, and I encourage everyone who's joining to utilize the Q&A box to direct questions to this discussion. So what is the current state of art of AI in your particular area, and where are we going next? Chris, let's start with you as our faculty director and leader for SAIL.
Thanks, Erica. So my area of expertise is natural language processing, and around 2020, there's actually a really easy answer for that one. So really starting in 2018, enormous progress has been made by using very large pre-trained language models. And so that started off with Elmo, and then there's BERT, and then there are various other ones with funny or less funny names coming from Sesame Street, of Roberta and Electra is one we were involved with at Stanford. But these models are, you're training over a huge amount of data simply to be able to predict words and context. But that's proven to be an extremely effective way to build up general knowledge of human languages. And they give a base from which you can then build all kinds of NLP applications. It then doesn't matter if whether you want to do text classification, question answering, customer support, named entity recognition. You can essentially use them for anything in natural language understanding or generation, and they just work far better than the methods that preceded them. So to some extent, what companies that are trying to stay at the state of the art are doing around 2019, 2020 is ripping out whatever they used for NLP before and replacing it with new models based on these large pre-trained language models.
And Emma, how about you? What is the state of art in your area of AI, and where do you think we're going next?
My area of AI is reinforcement learning, where we think about agents that learn by doing. And I think it's been a really exciting time over the last 5 to 6 years, thinking about what these can do, often in artificial environments like video games or for the board game Go, or in places where you have a lot of control like robotics. But I think one of the things that's been noted a lot in the field is that often some of these methods are somewhat brittle when we want to use them in general, and then there can be a lot of instability. And so we want things to be highly robust and reproducible if we want to be able to use these in a lot of high stakes domains or domains involving people like customers or patients or students. And so I think it's been really exciting over the last year or two to see a lot of people starting to think about, including our lab, starting to think about these challenges of both from the theoretical side, how do we have methods that are provably robust and that we have confidence in them so that when we deploy them, say, from using some prior data set, we can know with high accuracy or high assurances how well they'll do in the future. And as well as that, thinking about things that can work in sort of when we don't have a lot of data, when we won't always have that.
Tengyu, what have you been seeing?
Yeah, I guess my area of AI is mostly machine learning, deep learning, and the theoretical aspects of machine learning and deep learning. I guess we have seen quite some more understanding about how deep learning works, and also some of the technical improvement about how we train deep learning models so that they can generalize better. I guess in terms of the algorithm side, there are better and better algorithms that train deep learning models faster, but not much faster yet. So still we have to spend a lot of compute to do the deep learning models. But on the other hand, on the statistical side, I guess there are many more different ways to make your model generalize better on small data or even on large data, and also generalize better across different domains. For example, you train on one domain and you want to test on other domains. There are different ways to leverage the unlabeled data to generalize across domains. I guess, this is a kind of like both a kind of an issue for machine learning, but also it's a kind of opportunity. So currently the difficulty is that, when you have a quite different domain, then the model doesn't work as well as it is, in a training environment. But on the other hand, there are a lot of opportunities to improve these models to make them more robust and more kind of reliable.
And Samir, what have you been seeing in the industry side? What are companies implementing, and what are they looking for next in the broad field of AI?
Very good, thanks. And first of all, it's a pleasure to be in this group. The intellectual horsepower of this group is so high that it's a little bit overwhelming. But I would say this, as I was preparing, and I asked the organizing team from my side and said, had the Stanford AI team developed some AI models which can rifle through the panelist notes ahead of the time? I hope that's not the case, and the technology hasn't advanced so much. So, but with that preamble, I think Vatusa overall, we are a digital engineering firm. Just to introduce the firm very quickly, we pride ourselves in enabling our clients' digital engineering journey. We treat speed as a currency now. Most customers are trying to accelerate the journey, whether it's a customer journey, whether it's their operational transformation journey. We really help the clients in that light. Coming to your question, I think there are two parts to this discussion. I think from an industry perspective, the AI is going mainstream at this point in time. And the good part is that clients are talking about in next 3 to 4 years, about 75% of the clients will embrace AI, from operationalizing AI, from a pilot AI to really operationalizing AI in the client industries. And that's true across all industries, whether it's banking, healthcare, telecom, or media. But the not so good part is that the ROI of the AI programs today is low. About 45% of the customers are saying this is not yielding the benefits that we expected it to yield. And it's quite obvious because the data quality in most of the enterprises is not very high. The systems are still antiquated. So the throughput that is coming out of the AI systems, even in the most modern technology, is not that high. So that's where the industry is at. From a client's perspective, I think there are top three trends I would say that we're seeing. Number one, of course, is the frictionless customer journey trend. How do I make my contact center more efficient from an AI, leveraging AI? How do I make my entire consumer journey more frictionless? Is really a big trend that we are seeing. The second trend we are seeing is around operational transformation. Really use AI as a lever to drive productivity, reduce time to market, drive better agility in the enterprises. That's a sort of second trend. And third, I would say in the last 2-3 years, Erika, is what we're seeing is really the concentric circle, right? Customers started with AI as a BHAG, and then now they're going down from machine learning to deep learning. I think that penetration is beginning to happen slowly and gradually. Those are, broadly speaking, I think those are trends we are seeing.
Thank you for those insights. For our panelists, if you open up the Q&A box, you can see a lot of the questions that are coming in from our audience. Let's start off with one from directed to Professor Manning. It seems NLP is focusing more on word embedding after the transformer architecture, and character embedding is not used much these days. Is that correct? How do you see the use of character embedding use case for NLP?
Hey, that's a specific question.
We'll have a mix of specific and broad
NLP
for sure.
fans out there. So I think the truth is halfway between that. Yeah. So in sort of quote unquote early deep learning, which, for this NLP context is mainly meaning kind of the early years of the last decade of sort of 2010 to 15 or something, so the mainstream was, yes, we had words and we built up word vectors and they were super useful. But they had the limitation that there was a different vector for each word, and you weren't getting any sharing between related word forms, which are commonly the different forms of a word that have different forms. So something like run, runs, running. And that's only a little bit of a problem for English, but in many, many languages of the world, nouns, verbs, adjectives have many different inflectional forms that tell you about agreement and case and various other things. And so that started to lead into the development of character-based models, and quite a bit of work was done to get better generalization with character models, sort of mainly centered around 2015 to 17 kind of period. But around the same time, people also developed what sometimes gets referred to as word piece models, or sometimes it's just referred to as BPE, which refers to a particular method that's used to build them, called byte pair encoding. And so for word piece models, effectively you're using a simple clustering technique to find common subsequences of characters. So one of the advantages of this is it doesn't matter whether your language has spaces or not. So it works fine with Chinese or Japanese or Thai or something like that. So you're just starting off with your big long sequence of characters, and then you're starting to clump common subsequences of characters that you find in the input. And so the end result of that is that in your word piece, you might say, I'm going to have, 8,000, 16,000 word pieces. So anything that's a very common word will just become its own word piece. So, words like the, or even sort of ones that aren't as common as the, but something like, person, talk, those will become a word piece. But your minimal word pieces are individual characters, but commonly the word pieces you're working for uncommon words will be sort of small groupings of about 3 letters. So you might have a word piece for PAR and another one for, EN and one for TAL. So you could then build up parental from those 3 word pieces, even though parental isn't in your small vocabulary by itself. And it's just proven that that word pieces seems kind of a sort of an ugly hack in some sense, but it's proven to actually work super duper well. And it's just been a really useful and flexible middle ground between whole world word models and individual characters, because you're sort of mainly working with these sort of piece of a word units that often have a reasonable amount of meaning, and you're getting the common words as part of your word pieces anyway. So most of these big new pre-trained language models like BERT, Roberta, etc., are working on word pieces. So they're in that halfway in between ground.
Seems like it has a lot of relevance too for bringing back memories of studying for the SATs, many, many years ago. So I'm sure your kids probably did very well on their SATs. To Tengyu and Emma, we have a question that's regarding sort of, I guess, changing distributions of data. So we all know the distribution in real world keeps changing day by day. In order to give out consistent and safe action to the user, how would you suggest to update the RL model or any approaches to handle those states with constraint? How do you detect the distribution changing by comparing with the training set?
I think that's a great question. I think there's a lot of different interesting approaches to it, and it'll be great to hear Tengyu's discussion as well. I think that some of the things we've done before and some of the approaches in the literature, thinking about change point detection and trying to explicitly model the dynamics of the process, and then you can see whether or not there's a significant difference in the distributions over time. So that's one way where we're hoping we can actually detect it fast enough to know when you should start to actively retrain. I think another approach is to think of this more like a sensitivity or robustness, which is you can design policies, decision policies or strategies, which you think are going to be robust to a certain amount of deviation in the distributions. And I think for some areas, like maybe the news or things like that, it might be very hard to do that because there's huge differences very quickly, particularly right now in terms of the topics that are most salient to people. But in other areas, perhaps things like Amazon and customers, there's not going to necessarily be enormous shifts in most of the things people are buying day to day. And so in those cases where you think your distribution shifts are going to be smaller over time, then you can design policies that sort of should work well with constraints about how far those new distributions might change. And so I think depending on whether it's easy to retrain and how what's sort of the computational budget and how much data is coming in, I think in some cases it's very feasible to retrain really frequently or identify the change and then retrain, or even proactively retrain. And then in other cases, I think where the deployment itself might mean that you don't get access to that system for a while. So for example, in our lab, we've done some work on educational tutoring systems for children in conflict regions, together with our collaborators, War Child. And they're often giving kids iPads or devices or tablets, and then they'll only see that tablet again in like a month or two. So you can't just retrain every night. There's not the bandwidth. You don't have access to the devices or Wi-Fi. So in those cases, we need to sort of have things that are going to be more robust to any distributional shifts. In other cases, if you're Amazon, it's very feasible to retrain very frequently.
Yeah, and imagine a lot of the larger shifts are easy to identify, like, COVID and shelter in place. We know how much that's causing drift on our data. Tengyu, any thoughts?
I don't think I have much to say in addition to Emma's wonderful answer. So I guess just to mention one slightly another idea could be that you can also retrain with unlabeled data. This is something recently that is somewhat popular, like it's called self-training. So I guess when you retrain, a technical decision you need to make is whether you want to whether you want to collect more data on it, right? So like more labels for your data. So recently people have found that you can actually self-train on the pseudo labels you have. Like pseudo labels meaning you use your current classifier to get the incorrect labels actually, right? So many of the labels are incorrect, but you can still retrain on those incorrect labels and get some benefit out of it. With Percy Liang and our student Anaya Kuma, we have a paper on this showing that you can do self-training online without any new labels and still get better in performance. But of course, when a shift is too big, then this method stop working. So there is a limit. As Naima said, if your shift is too small, then you probably should be. If it's relatively small, then probably should be robust at the first place. And if your shift is very big, you probably should retrain. And maybe in the middle, you can do some self-training as well.
Maybe we can take a minute and expand on that a little bit further. These sort of scenarios where labeling isn't available and then we're stuck in this small data environment. This has come up a lot. We talked about it briefly this morning about the challenge of getting labels, and I'm sure there's whole industries that are popping up on labeling data in one way or another. Are there real examples where techniques like zero-shot learning or these other new methods are currently being applied? Any thoughts?
I think I'm sure there are probably some cases where zero-shot learning can be applied. Although I guess maybe it's kind of like cost-benefit analysis in some sense, right? It depends on the context. So maybe typically like a few labels are not that expensive. Maybe I don't know, like depending on the situation. So I guess maybe the most in the very near future, maybe the most realistic setting would be somewhere kind of like a few shot learning, maybe like zero shot might be a little bit too ambitious in my opinion. But of course there are cases that you have to use zero shot learning, then you just do it. So but generally in any cases it doesn't matter how many labeled examples you have. I think there are recent new techniques that can do better than the naive method. So I guess there are still high room that we can improve upon them.
And I suspect this came up this morning, but like Chris Ray's group has done a lot of really beautiful work on thinking of how do you get labels more cheaply? So you can have sort of these labeling functions that then make it much faster for people to give sort of approximate labels for a lot of data. And they've showed that that can often work really well as a way to reduce the cost of labeling.
Samir, have you seen this as a challenge with your clients in an industry where the biggest hurdle is this area of labeling your data?
Yes, Erica, yes, we do see it all the time. And honestly, people have been innovating around this in the industry. And I think we've seen broadly two approaches to address this. One is really what I call as a more bottoms-up operational approach. So I'll give an example of an insurance company. They were getting on their 0800 call number consumer reports. and they had a flood of those calls, and they were trying to label the data. So they put a small team to collect the data manually first, and then really extrapolate the data out to really draw some insights from it. That approach is a little crude, but works in certain scenarios. But more importantly, where the industry is now heading towards with this is they can take a second approach, which is much more rule-based. So as an example, for one of the banking clients, they had reams of data coming out of their IT infrastructure, the server logs, the router configuration, and so on and so forth. So what they did was to find which equipment is faulty. They started reading the log files and then labeled the data back using the patterns and the deduction from the data itself in a reverse way. So that's how they're labeling it out. Candidly, from an industry perspective, there isn't a very clean solution. People are either going the manual route of operational people and investments and labeling it up and then supersizing the data set, or doing some rule-based configuration to derive some labels. That's how we see. But I think it's a great area for industry and academia to collaborate together and really work out some more industrial strength solution as we move forward.
Yeah, go ahead, Chris.
Yeah, I'll give a different answer. So I think in general for, most of whatever the last 20 years of machine learning, I would have given all of those answers and they've been sort of right. But so my answer to every question is going to be large pre-trained language models. But there's sort of actually, I feel, an interesting phenomenon that's happening right now with these huge pre-trained language models, that they are actually giving a very different avenue that gives a very different answer. So and so sometimes people say these huge pre-trained language models are great zero-shot learners. And, in a sense that's true, but in a sense you have to hold on to your wallet because you're sort of redefining what zero-shot learning means when you're using that terminology, since really what it means is that they're sort of really great example-based learners that can map this new data onto existing stuff that was somewhere in their training data. But nevertheless, to take a concrete example of that. So, a common thing that people want to do, that's common but simple thing in industry is text classification. And well, traditionally that was, this kind of hard, don't have the data situation of, oh, gee, we'd like to map things onto these, hierarchy of 48 classes we've got. Do you have any data? No. Well, you could either start to write rules or you could start collecting data, and you'll need a lot of data. It was hard. Whereas it's honestly the case now that you can get pretty good results by saying, well, I can use my big pre-trained language model. I can get a representation of the text using something like a sentence BERT model. I can just take the name of the class and encode it with the same kind of pre-trained language model and get a representation of the class, and then I can see how close together they are. And that doesn't work terribly. It actually works sort of decently as a starting point. And then there are some things you can do to do better. Commonly, class names are kind of at a different level of abstraction from the actual words people use for documents in a class. So if you can learn a single transformation matrix to map them closer to the right space, that can significantly improve your results. I mean, another trick that people have been using actually is, so there's been a lot of work on this task of natural language inference, where you have two pieces of text. You have a premise piece of text and a hypothesis, and you're typically wanting to say that this hypothesis either follows from, contradicts, or is unrelated to the premise text. And it's actually turned out that that framing has also worked well for this doing sort of zero-shot text classification, that again, you throw in the document as your premise, you throw in the class candidate as your hypothesis, and you see whether it says follows or or not, and you pick the class that best follows. That's been working pretty well. So all of these techniques, you can actually get a fair way with no training data at all. And indeed, you can get sufficiently far with no training data that you don't do better with just a teeny bit of training data. I mean, like, until, 3 years ago, I used to say zero-shot learning is stupid. There's no problem that people are interested in where somebody can't sit around for a day and label 20 examples of each class. Let's get real. The only interesting problem is few-shot learning. But in this context, doing that is useless. Turning up with 20 examples of each of 48 classes and say, hey, I've helped, it actually won't make things better than unless you can have actual significant data resources. If you can have lots of labeled data, then you can still do much better, but you really actually don't do better from only a little bit.
So we'll take another question from the audience, which may also segue us into a broader discussion. Can we talk a little bit about constrained exploration in reinforcement learning as well as potentially other applications, and avoiding taking unknown actions that may be too risky? So maybe this ties into a question that I had about how do you responsibly go from prediction to action, and how do you regulate that, and whose responsibility is it? So kind of maybe the more technical question of how do you do it, but then also what are the larger implications of using something like reinforcement learning where there might be some sort of risk attached to it.
This is something we've been doing some work on, and a number of others are really interested in this topic. I think it depends a lot on the domain and exactly what risk means in these cases. There's some cases where I think it's very high stakes, like intensive care units. And in that case, or similar domains where it's very high stakes. And so probably what we can hope to do is sort of try to use existing variability in the current data to identify things that we think are more effective, and then kind of have things which with high confidence are monotonically improving. And those are very conservative approaches, but you still might be able to get progress because there's still often minor variabilities in how people interpret protocols, or mistakes are made, but maybe those weren't mistakes if they lead to better outcomes. But that's a very conservative and a very slow approach. In controls and in robotics, often people have to make assumptions or do make assumptions about the laws of physics and safety and smoothness that allow you also to extrapolate. And people like Andreas Krauss have done some really interesting work in this space of saying, and Claire Tomlin too, and others, of like you start with some sort of feasible or safe region, and then you kind of slowly grow that out. But I think there are also a lot of other application areas where it's important. We don't want to waste data, but it's not quite that constrained. And so there, I think we can often be a little bit more aggressive in how quickly we can gather data, because maybe we don't know, like maybe it's an educational game and we're not sure which way of sequencing is actually most effective for kids. And so in those cases, using more aggressive exploration will be warranted. So I think that it really depends a lot on the domain about what sort of levels of exploration are valid or reasonable. And I think in general, as we think about deploying these things, I personally suspect that we're going to see more regulation and more sort of informed policy over what things are considered to be reasonable to deploy in society. And of course, we've seen a lot of movement on that recently in terms of bans on facial recognition systems. But I also think that it's something we talk about a lot as faculty, of how do we train our students to think about the ethical implications of the systems we build, because regulation often takes a while and we don't want it only to be reactive. We want to make sure that we're deploying systems that we think are effective at the beginning.
Samir, what's your perspective maybe from the industry side? I mean, you're kind of in a similar position as us academics, and that you're building these tools that other people are using. I'm wondering what you've heard or what you've seen, or how things may have changed over the past year or so as governments start exploring the idea of regulating these models.
Yeah, no, I think this is a very serious topic in industry, and I think enterprise customers take it very seriously. And I think, as you know, there is a vast amount of AI being deployed in consumer experience type activities, which is not very regulated. So I think it's okay If you're on an e-commerce site, a product recommendation comes up and it's not correct, it's probably fine. But when you come to some banking industry or telecom industry, which are highly regulated, or even healthcare for that matter, these are serious issues that the industry is grappling with today. I'll give an example. For example, in the sanction screening in banking world, there are individuals which are barred to be doing payment transaction or credit transaction, or even in businesses which can't be doing payment transaction because they are declared as sanctioned. So there is a feature functionality that industries have developed, and it is very regulated. And I think what companies have done, not only really invested heavily in terms of fine-tuning those models at one level, but they've also put internal structures, roles, and org design to augment those. And we are right in the middle of many of those conversations to really work with these people in the enterprise side, work with the regulators to make sure that the data recommendations that are coming out from some of these models is absolutely tested, because one wrong transaction can have a catastrophic impact on many of the corporations. So it is a very serious topic. I think it is evolving space right now. And like I said earlier, this is again another topic where industrial strength solution is still not there. I think people have augmented quite a lot of this activity through some manual controls, just because they have to, because the implications on enterprises are extremely high.
So we have a question from the audience that kind of about data types. So Tengyu, you talked about a method for images, and the audience member is wondering, is that valid for images only, or is it applicable to text numeric data? And maybe the larger question for the whole group is, for these more advanced methods, are there any data types that are particularly suited for them? I'm sure Chris Manning has an obvious answer for this, but maybe there are other data types that are not as suited for it, or maybe there's a better way of representing the data to get more value out of it.
I guess to answer the question, so we did test text and other kind of type of data, so they also work. So, but also as Erica says, so not all, it's not like it's supposed to be that one algorithm works for all the type of data. So for the image data, we know that we are very competitive. We are state of art. We can do better than on all the baselines. In the context, in the settings that we are testing. So for the language data, we only test, compare with pretty simple baselines. So and we do believe that there are ways to improve them by customizing the method to the special property of the text data. So so I think the short answer is that they should work better than baselines, but it's unclear whether they are the best one possible. So definitely, I think there are rooms to improve for text data by specializing the algorithms.
Emma or Chris, any particular data types or combinations of data types or structures that you see are working particularly well or particularly challenging for the methods you're developing?
Well, for what I've mainly been talking about for these large language models, well, text, or at least sequences of symbols, they work great on that. So one of the interesting things of what's happened with deep learning is that there's really a very small toolbox that's being reused in different applications. So there are convolutional neural networks which have been used for language as well as for images and video. And conversely, for all of these big language models, the kind of model that's used in them that I haven't mentioned actually the name of up until now, I think, is transformer models. And transformer models are actually a huge development, but they build on the work from the few years before that of attention-based architectures. So attention has been this sort of very powerful new neural building block, which is actually genuinely a new neural building block from the 2010s, whereas most of the other things that we do are really things that were invented in the 1980s or 1990s. So they've then been applied, also starting to be applied to vision tasks as well. So there is crossover, but nevertheless, the different modalities just are different. So there's just a good reason why CNN models dominate in vision, and there's a good reason why transformer models are very dominant now in sequence-based tasks like language. So if there's a thing that sort of seems like it's sort of underworked and explored, it's actually dealing with more structured data. So there has been work on structured data and looking at things like knowledge graphs, and so graph convolutional models have been explored quite a lot. But, you know, I think that area hasn't been very successful and hasn't been very explored, to an extent that for some of the tasks that are around the area of knowledge-based reasoning, people are getting better success at the moment by taking their knowledge bases, turning it into a sequence of text, and then running text-based methods to be solving their problems.
Emma, I don't know if you had any thoughts of different data modalities or any constraints in that side.
I think that what Tengyu and Chris said already is.
What about sort of online collection of new data? Do we need to be better about determining what data to collect, you know, from different locations and distributions, and what data to label as well? Any thoughts on that?
I think that's a really big issue. I was giving a talk at the Machine Learning for Health conference last week, and one of the other speakers was Zaid Obermir, and he was talking about the fact of the importance of the labels we choose to gather for data sets. And in particular, they had a really nice science paper talking about, which uncovered significant differences in an algorithm between African Americans and whites in terms of its effectiveness, because the proxy they were using for sort of health outcomes was cost. But if you might imagine that it might be that some subgroups are systematically getting less, support for their health on average than other groups, then if you just use cost as a proxy for health needs, you may be systematically underestimating health needs of certain subgroups. And that's exactly what they found there. And his point in his talk was really to highlight that whatever labels we use, whether that's for a reinforcement learning algorithm in terms of our utilities and our rewards, or in terms of how we're classifying, someone as like a high cost or high needs patient, is completely critical to the output we're going to get from the algorithms. And so it's really worth thinking very carefully about those and working closely with domain experts, as well as doing sort of these kind of high level qualitative or exploration, data exploration analyses to make sure that the labels that we're using are really the ones we want. In my field, we often call that reward hacking. So if we use a reward that is not really the reward that we want, so as an example, in a tutoring system, if we just try to make it so that students do problems quickly, the easiest thing for the algorithm to do is find one problem the student got right, and then you just give it over and over and over again. And because they're very likely going to continue to get that problem right. And so while getting problems right sounds like it might be a good proxy for student learning and progressing, it in fact is something that's very easy to reward hack and get not the desired behavior out. So I think this question is a really important one in terms of, as we go forward, how do we make sure the rewards and labels we use are really going to give us our desired objectives?
I see a couple of unmuted folks. Tengyu or Chris?
I'll make a comment. So, I mean, so in any real AI application, the fact of the matter is the world keeps changing, and so you want your models to keep changing to keep up with the world. And so, a lot of the time for the sort of academic papers you read, there was some fixed data set and they trained on that and they did some different stuff and the numbers went up. But that just isn't a good model for the world, where you want to be in a dynamic process where you're regularly updating your models to correspond to what's happening. But, something that's been observed is that you also have to be careful when you're doing that, because once you're in this situation where you're sort of regularly sort of using your models and updating them, you can have bad feedback. And so you really have to be careful not to have problems there. And so that's the sense in which all learning problems turn into reinforcement learning problems. And Emma should give the answer.
And that's been something that there was a nice best paper in ICML a couple of years ago, the International Conference of Machine Learning, talking exactly about the issue Chris is highlighting of how some of the algorithms, even ones perhaps focused on bias or fairness, might have unintended feedback loops. And so thinking about the sequential. Now, of course, as Chris points out, the dynamics process of the world is really, really complicated. So it's not clear we'll be able to plan and optimize for it perfectly. But I think RL is a useful framework for thinking about the downstream effects potentially of the decisions we're making now.
If I may quickly add on this. So how we are solving this problem from an industry perspective is fairly unique to what you said. It comes back to our engineering DNA. So we build this platform, which we call as platform AI. And these are very domain-centric AI platforms that we built. So one for healthcare, one for banking, one for media, and so on and so forth. And in each of these platforms, what we do is really inject a lot of synthetic data from external sources to the point that you made, and keep injecting and keep training that data to make our models better. Now, on top of it, what we do is really apply the work that we are doing with your team, the data Shapley part, to really make the data more efficient and really make sure that those practices can reduce the quantum of data, but keep injecting more data and filtering up and make it more efficient as we go forward. The second part we do is really bring in elements of computer vision to it, so that the images, especially in the healthcare industry, that are really important, even in banking industry. You know, there was a time when you will scan a check through an OCR, and that was good enough. But now people really want to dissect the check down and say, who's the customer, what transaction they're doing, what kind of microsegmentation we can do. So it's getting more and more intelligent, and our platform, AI platform, really allows customers to do that. And then the third part of that is really to really allow customers to use all these attributes to do innovation on top. One of the problems that industry is facing is to how to avoid biases on data. How do I make sure privacy is protected from a GDPR perspective, and otherwise as well. And some of these things we try to aggregate up using the industry data on our platform AI, so that we can help our customers in a very systematic way, in a very engineering way, help them onboard some of these newer techniques as we move forward.
And for those of you who were listening, that was some of the work that Prof. So has been doing with Virtusa. He presented earlier this morning about the value of data. And so we really appreciate the opportunity to get feedback on how these models work in the real world. So thank you for that. Let's see, what about, I guess we sort of talked about this with labeling, but what about dealing with unbalanced data? I'm sure this is a huge issue in reinforcement learning, probably also in natural language. How do we deal with situations where, you know, the prevalence of some sort of really important event is extremely low? You know, how do we address those sorts of issues of unbalance in the training as well as in, you know, real-time learning opportunities? Emma, I saw you unmute yourself if you want.
Oh, I was going to say, I was about to direct it to Chris or Tengyu first, because I think it's particularly a big issue there. I mean, it's certainly an issue in reinforcement learning too, but I'd be curious to hear their thoughts on the supervised and unsupervised learning to start. Well, supervised learning to start.
Yeah, so I guess, Emma can comment more on the reinforcement learning side. So for the supervised learning side, I guess the kind of techniques that we are currently trying to work and also propose is kind of like what I gave in the talk. So we are trying to use regularization techniques to help regularize the rare data so that you get better generalization. So the main issue is that often when you have this imbalanced data set, there are two issues. One issue is the training. So the rare data don't get trained very well. So sometimes they don't even, your model don't even fit to those rare data just because they have a smaller presence in your data set. You don't go through those examples very often. So then you don't fit those examples very well. So these kind of issues can be solved by some of the kind of classical ways, like a resampling, reweighting. You can weight up those rare examples or resampling more often those rare examples. But this doesn't solve the generalization issue in the sense that those rare examples often have worse test error than the frequent examples. So, so the basic idea is to regularize the part of the space of the rare example so that you use a more smooth and more kind of like a simple model for the rare example so that the generalization can be, accuracy can be better. So of course there are other techniques. For example, you can collect more data to balance it, or you can do other kind of things. But regularization is one of the ways that we try to address it without getting more information. So this is like a technical way to address it. I guess that's, yeah. I guess maybe another thing is that, just to think about some other options. Like other options is that you somehow can use the frequent data to help the rare data. This is something we are trying, but I guess this is more relevant for unsupervised learning probably, which or like a language model and pre-training kind of things that Chris is more familiar with. But the general kind of idea is that you say you learn a lot from the frequent data, some kind of features or some kind of like a important aspect of data, and then use a small amount of like rare data to do the part of job that you really care about, something like that. Yeah, I guess I would like to Emma and Chris comment more on this.
I mean, I guess in my case, I think of it more in terms of kind of the exploration problem and the data coverage problem. Like where either if you have existing data sets or if you're collecting online, if some things are really sparse, like if you have to take a particular sequence of actions for your robot to get to the goal, or like it's kind of a combination lock type examples, then you often need a lot of data or very strategic exploration in order to get the data you need to identify what the right thing is to do. If you're in other cases where there's sort of lots of good solutions and you're happy to be sort of satisficing with respect to one of those, which I actually think is pretty realistic in many cases. Like in most real world cases, we don't know what optimal is. And so there might be sort of a sufficient improvement for us to be willing to deploy something new. So it's sort of a bit different because one of the great things about RL is that we're actively in the online cases collecting the data. And so we can try to kind of drive the system towards parts where we'd like to get more data, which we think will be more promising.
I don't think I have a special answer to give. I mean, in practice in the real world, a lot of the time, what you do is you sort of just change the sampling. So you sample much more frequently the rare stuff, so it's nearer to balanced, and hey, it learns better. But, the kind of techniques Tengyu was talking about were then sort of better ways of solving these problems.
So we are running out of time, and there's a number of still open questions. And so we'll try to address those offline and get back to those of you who weren't able to have your questions answered. I think we should probably wrap things up with hearing from each of you about a little more about what's next for you and for your lab, or for TUSA. Maybe we should start with Samir.
Sure. First of all, this is a very interesting and very enriching conversation for me, Erica and team. And I think one of my clients summarized it very well, so I'll put it out here. They said, we like artificial intelligence to be more intelligent and less artificial. And what it really meant was the data that is out there, we don't want more synthetic data, more artificial data. We want it to be more intelligent. I think a lot of the conversation we just had was around small data or labeling of data, or all elements towards that. And I think from an industry adoption perspective, as we move forward, we look forward to partner with you guys to really see how we can get to the journey of less artificial and more intelligent.
We'll go in reverse order from where we started out. Tengyu, what's next for you and your lab?
I guess part of my lab is doing theory, trying to understand deep learning. And I guess the practical part of my lab are mostly, I think one of the main things we are trying to understand right now is uncertainty quantification, which in my opinion, think is kind of one of the important things in the center of several questions like domain adaptation, transfer learning, even reinforcement learning. So in the sense that, for example, if you want to transfer to new domain, you want to know whether you have to do this transfer, right? So whether you have to collect new data for the new domain. So you have to know that whether you are doing well for this new domain, or you have to even see whether this is a new domain by estimating the error, whether the error drops in a new domain. And for reinforcement learning, I guess a technical thing is that for many kind of like efficient exploration strategies, we need to know the uncertainty of the world in different science. So quantifying uncertainty seems to be, at least one of the shared techniques in some of these different areas. Also for active learning, for I guess even just answering quantification itself, would be useful for many things like for safety and like risk sensitive kind of environments. So I think that's one of the technical directions we are trying to pursue in the near future.
And Emma, how about you and your group?
I think a lot of the work that we do in my group can sort of be summarized by the idea of learning from limited data to robustly make good decisions. It's been really exciting to be in this area. I think the last few years and going forward, I think there's going to be so much focus and excitement over how do we use AI to make decisions. I think in my own lab, one of the things that as I also do a lot of theoretical work, but the theoretical work that I'm really interested in right now is thinking about how do we have algorithms that are robust that we can deploy and that sort of satisfy some of the challenges we see in the real world, like the non-stationary and constant changing that we talked about just now. But as well as that, we're always making modeling choices, even with deep neural networks. And so how robust are our methods when we make poor modeling choices, or modeling choices we might not realize are poor, but actually don't fit our data well. And I think that as we think about trying to democratize AI, we really want systems that don't require you to have a PhD in AI or an RL or NLP in order to deploy these things successfully. And so we need algorithms that can kind of adapt to the data and are robust to sort of different forms of misspecification. And so I think that's a really interesting both algorithmic challenge and technical theoretical challenge. And the other thing that we haven't talked so much about today, but is a big area of interest for me, is that I think it's also really exciting to think about AI augmenting people more. So how can we do more like workforce support or learning support or sort of decision-making support in a way that is really amplifying human goals, and how do we do that in a way that's going to require like intent understanding, it's going to require natural language processing, it's require sort of RL to help people to reach the goals they want to. And I think that'll be work that we'll want to do in collaboration with our sort of HCI colleagues a lot.
Yeah, I've been thinking about your work with childhood education a lot as I try to get my kids to stay focused on their different platforms. So I imagine that will continue to be a big and motivating application of your work. Professor Manning, where are you guys going next in your group?
Maybe I'll be able to give an answer that also touches on one of the unanswered questions. So one, not the only area, but one new emphasis that we've been looking at is looking at doing dialogues. And, notwithstanding what I said about how marvelous these big pre-trained neural language models are, I mean, the reality of 2020 is that we don't really have machine learning based dialogue systems for anything much. That basically the sort of standard task-based dialogue systems that companies and businesses use are basically still handwritten dialogue trees with a little bit of machine learning sprinkled into them. So you sprinkle in some machine learning text classification to say, is this, a billings return or new purchase requests that they're making, and you can sprinkle in some machine learning to fill in some slots as to, given what they've said, to identify which words express the product name or the price. But basically the overall flow of having a dialogue system is still very much this hand constructed thing. And so an interesting challenge is how can we actually get more of higher level planning and control being done in a more of a neural model of a dialogue system, or to at least partly more be able to be using some of the good things that have come out of our neural language models in more of a dialogue system. So one thing we've been looking at is less on the task-based side, but on the social chit-chat side. So several of my students took part in the Alexa Prize, which was a social bot competition in recent months. And, even that sort of seems like it's an environment that really plays towards just using big neural language models. But, even then, it's actually hard to do it at the current moment, because it's easy to get neural language models to produce text that, is grammatical and is sort of coherent, but it's very hard to actually have high level control where you can direct where the conversation is going, and how can you go about doing those things. So that's certainly an area I'm interested in looking at more.
That's great. Well, I want to thank all the panelists today and our faculty for submitting your talks ahead of time. It was great to be able to listen to them, and the recordings I think really helped with consistent audio and that sort of thing. So we really appreciate it. I also want to take a moment to again thank our members. Earlier today, I announced that the amount of funding that's come in from our corporate collaborators has funded the equivalent of 75 PhD years, which is huge, and we really appreciate it. We also really appreciate all the insights about how the algorithms and techniques and methods that are developed at Stanford work in the real world. So we really appreciate you all for giving us that opportunity and that feedback, and we look forward to more.